Welcome to Lecture 22, Unit 4. This is the central limit theorem, and my name is Jorge. So the objective for Lecture 22 is that we're going to use the central limit theorem to solve problems involving sample means for large samples. So the first thing we're going to talk about is distribution of sample means. So let's say the researcher selects a sample of 30 adult males and finds the mean of the measure of the triglyceride levels for the sample. He then repeats this process for 100 samples. Then the mean becomes the random variable that constitutes what we call a sampling distribution of the sampling means. So again, he selects a sample of 30 adults, finds the means of the measures, then he repeats the process for 100 samples, and then he gets a sampling distribution for the sample means. So sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. So if the samples are randomly selected with replacement, then the sample means for the most part will be somewhat different from the population mean. And now these differences are caused by sampling error. So sampling error, this is simply the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. So what are some properties of distribution of sample means? The mean of the sample means will be the same as the population mean. The standard deviation of the sample means will be smaller than the standard deviation of the population, and it will be equal to the population standard deviation divided by the square root of the sample size. And we'll talk about that a little bit later. So here's an example. Suppose a professor gives an 8-point quiz to a small group of 4 students. Now, the results of the quiz were 2, 4, 6, and 8. Now, assume that the 4 students constitute the population. So the first thing is we're going to find the mean of the population, which is the class. We're going to find the standard deviation of the population, again, which is the class. And then we're going to find the sampling distribution of sample means if sample of size 2 are taken. So remember, there were 4 students, so we have 4 scores, and that's the entire population. And then we're going to go ahead and find the sampling distribution of sample means by taking a sample size of 2. So before we do that, here we know that we got scores of 2, 4, 6, and 8. And this is what we call a uniform distribution. And it's a uniform distribution because you see that the frequency for each one is the same. So from this data set, we're actually going to get something that looks like it's normally distributed. So the first thing is we're going to find the mean of the population. The mean of the population is just 5. So these 4 students, we got all their scores together, and they got an average score of a 5. Now the standard deviation, or sigma, is 2.236. So we're going to use this information to be able to do the sampling distribution of the sample means. So here we have some samples of size 2. So for the first sample, and of course we're doing replacement, so it's a 2, 2 is possible to get, right? So the first sample was 2, 2. It had a mean of 2. The second sample was 2, 4 with a mean of 3, 2, 6 with a mean of 4, and so on, right? And so these are all the samples that we got. And so from here, we're able to find the frequency distribution. So the frequency distribution gives us this. So X, when the mean is 2, that occurred 1 time. The mean is 3, that occurred 2 times, and so on. And you can see here that looking at this frequency distribution, that it looks like it's normally distributed because it goes 1, 2, 3, 4, and then 3, 2, 1. Now, the mean of this sampling distribution of the sample means is actually 5. And that's the same mean that we had when we just got our population, which was just the class. So here's the frequency distribution. The mean is 5. And then here we can see the sampling distribution of sample means. Now, looking at this histogram, we can see that it is, in fact, normally distributed. So we can see that sample mean, the mean of the sample means is, in fact, 5, which is equal to the population mean. The standard deviation of the sample mean, denoted by sigma x bar, is actually 1.581, which is equal to the population, to the population standard deviation divided by the square root of 2. Now, if you remember, earlier we said that we're going to the standard deviation of the sample mean is going to be equal to the population standard deviation divided by the square root of the sample size, and the sample size that we took here was 2. So when we divided that, we actually get 1.581. So if all possible samples sample of size n are taken with replacement from the same population, then the mean of the sample means equals the population mean, and the standard deviation of the sample means is called the standard error of the mean. As the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. As previously shown, in this distribution will have a mean mu and a standard deviation of sigma divided by the square root of n. Now, if the sample size is sufficiently large, then the central limit theorem can be used to answer the questions about the sample means in the same manner that a normal distribution can be used to answer questions about individual values. The only difference is that the new formula must be used for the z values. So instead of using z is equal to x bar minus mu divided by sigma, we use z is equal to x bar minus mu divided by sigma divided by the square root of n, which is the sample size, sorry. Now, it's important to remember two things. When the original value is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. When the distribution of the original variable might not be normal, then a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, the better the approximation. Now, recently, there's been a lot of discussion where even a sample size of 30 might not be sufficient. We won't get into that in this course, but just to be aware that if you do take other statistics courses after this one, you might get information that's slightly different. So here we have some graphs that kind of shows us what the central limit theorem can do. So the first one here, as you can see, is that we have a shape here of the distribution, right? So as we take sample sizes larger and larger, you can see that the distribution starts becoming more and more normally distributed. So when we get to n equals 30, we actually end up with a nice bell curve. Again, the central limit theorem allows us to use the 68, 95, and 99.7 information that we used previously, where then 68% of the data points will be plus or minus 1 standard deviation, 95 will be plus or minus 2, and 99.7 will be plus or minus 3 standard deviation from the mean. So here's the first example. Now, the average amount of purchase at a newsstand is $2.12. Now, the standard deviation is 45 cents. If 25 customers purchase items at a stand, find the probability that the mean of the purchase is greater than $2.30. Now, let's assume the distribution is, in fact, normal. Now, for this one, we're not able to use the website because our z-score formula is slightly different. So here, mu is 2.12, sigma is 0.45, n is 25, and x bar is 230. So using the formula for z, we can actually get what the z-score is, and the z-score is actually 2. So using the distribution tables, we find out that the probability that someone spends more than $2.30 is about 2.3%. So 2.3% of the customers at these newsstands, will spend more than $2.30. Another example, the average lifetime of smoke alarm manufactured by a company is 60 months, with a standard deviation of 12 months. If a sample of 36 smoke alarms is selected, find the probability that the mean of the sample will be between 57 and 62 months. So here we have our mu is 60, sigma is 12, n is 36. Now x bar 1 is 57, x bar 2 is 62. So we're looking for the probability that will be between 57 and 62. Now, finding the z-score for each one of these, we're finding the probability that z will be that negative 1.5 less than z less than 1. So what is the probability of those two? And so for the first z-score, we get a 0.4332. For the second z-score, we get a 0.3413. So together, we get a 0.7745 or 77.5%, not two decimal places. So 77.5% of these batteries will have a lifetime of between 57 and 62 months. Here's another example. The average number of pounds of meat a person consumes in a year is 218.4 pounds. Assume that the standard deviation is 25 pounds, and then the distribution is approximately normal. If a person is selected at random, find the probability that a person consumes less than 224 pounds per year. And then if a sample of 40 individuals is selected, find the probability that the mean of the sample will be less than 224 pounds per year. So for the first one, probably if someone consumes less than 224 pounds per year. So we have mu, sigma, and x. So we're going to use z. So we get 0.22, which is about 58.7%. So the probability that we randomly choose someone and they consume less than 224 pounds is 58.7%. If a sample of 40 individuals is selected, find the probability that the mean of the sample will be less than 224 pounds per year. So using this information, we're going to use the z-score or the z value using this formula. We get a z-score of 1.42, which we get about 42.2%. Now, that we add to the 0.5, and we get about 92%. So there's a 92% chance that in a sample of 40 individuals, the probability the mean of the sample will be less than 224 pounds.